Hello and welcome back to Apt for You. In this particular video, we will be discussing about a new approach of solving the pre-order traversal, but this time we are not going to use recursion, right? So basically, this particular problem deals with solving the pre-order traversal, but with a non-recursive approach, right? So we know that when we were using pre-order traversal with recursion, that particular time we were basically using because basically the recursion was making the use of stack, right? And we are also familiar with how pre-order traversal works with recursion. In this particular video, we will focus on the non-recursive approach and how actually that can be achieved. So before proceeding further, I would like to go through these sentences because the algorithm is hidden here only, right? So we know that in the recursive version, a stack is required as we need to remember the current node. This is the idea, right? Why do we need a stack to remember the current node's address? That is why in recursion the stack was being used, right? So that after completion of the left subtree, we can go to the right subtree. So basically what happens in the recursive approach was, we were provided with this address of this particular head node or root node, and then we were trying to print this particular value. We printed this particular value 1. Then we performed a recursive call wherein we want to perform the pre-order traversal of the left subtree. The moment pre-order traversal of the left subtree was completed, the control comes back to this particular node, and then we perform the pre-order traversal on the right subtree. So why do we need stack here? The reason why we need stack here is because once we return from after performing the left order traversal of this particular node's left subtree, now we need to basically find point to this particular node's right subtree, right? Now how will you point to the right subtree of this particular node if you don't have the address of this node, right? That is why for future purpose, okay, so in order to ensure that in future I would be able to access the right subtree of this particular node, I should be basically storing the address of this particular node in the stack. That is what this line basically mentions. Now the purpose of non-recursive approach, how can that be achieved? So basically, to simulate the same, first we process the current node, right? The current node will be processed, means we will be printing its value. Then before going to the left subtree, we should ensure that the root node's address is stored in the stack. So we store the current node on the stack, right? This is algorithm. Step 1 is this, processing the current node. Step 2 is this, store the current node on the stack. What is the third step? The third step says that after completing the left subtree processing, we pop the element and go to the right subtree. This is the third step, and we shall continue this process until stack is non-empty. So what are the processes? First of all, printing the current node value, okay? Then before going to the left subtree, we should basically store the address of the current node in the stack, on the stack. So we will be using stack basically in the non-recursive approach also. After completing the left subtree processing, what happens is we will basically pop an element from the stack, and now if we pop the element from the stack, we will basically get the address of the root node, and then using that particular root node's address, we can basically point to the right subtree, right? And this way basically we can continue the process until our stack is non-empty, right? So now the question is, how can we implement it? So we shall now jump into the coding part, right? How can this particular problem be solved using a non-recursive approach? So basically I will take you to the coding section. So if we focus on the Geek for Geeks problem, right, there is a problem available on Geek for Geeks. I will be using the same for explanation. This problem says that we have to basically perform the pre-order traversal using an iterative approach, that means non-recursive approach. And the problem strictly mentions that our task is not to read or input anything or print anything. We just have to complete the function preorder, which means this particular function we have to complete it, which takes the root of the tree as input, clearly visible. The root is taken as input here, and returns a list containing the pre-order traversal of the tree. And this will basically return the list containing the pre-order traversal of the tree. Please focus on this particular line. We have already dealt with this situation in the previous video, wherein we know that generally our algorithm says that during pre-order traversal only we will be printing the root node's value, right? But now you don't have to print them during traversal. You better store them in an array. So for that particular purpose, what we will be doing is using a vector array. So yeah, let me just zoom the screen. I hope things are fine. Okay. Alright, so let us see what we will be doing. So as we know that we are going to use a vector array, so let me create a vector array which will be of integer, obviously, because it is going to store the values of the nodes, right? And the name will be suppose output. Fine. So vector integer output is the name of the vector array that we are using. Now we have also discussed in the previous video that whenever we are doing pre-order, generally it was void in nature, right? Because the function was basically void, and inside the pre-order function only we were making recursive calls and printing the nodes value, right? So but here you see the pre-order function that they have been providing. Now this is going to return a vector array, right? This is going to return a vector array, but generally we know that the algorithm says that this particular function should be actually be void, and it should be generally be void, and inside the void you have to perform the traversal. So for simplicity, what we will be doing to deal with this particular situation, I will be declaring another function solve, right? So I will be declaring a function solve. I will be passing a root node to that particular root nodes attached to that particular function solve. Now this particular function solve will basically be void in nature. So let us define the function solve. Void solve. Now you can assume that this void solve function is similar to the preorder traversal, node star root, right? So this particular function solve will receive the root node address. So got it. Now what is going to happen? So let me just draw the diagram here of the tree. So we have 1, right? We have 2, 3, 4, 5, 6 and 7. So now since we are going to solve this particular problem using a stack, we know that we just now discussed that we are going to use the make the use of a stack. So basically we should first of all declare a stack. So stack, now what type of stack, what type of values basically it will store? It will be storing the address of nodes. So stack node star, fine, and stack. So the stack is declared. Now what next? So basically what happens next is, alright, so we declared the stack. Now what next? So basically what happens is, now we understand why we basically require stack, because we know that initially the root node is pointing to this particular node, right? And the algorithm says that the moment root is pointing to this particular node, first of all we basically print what value is present at that particular root node. So basically normally what should happen is we should do cout root data, right? Cout root data. But since we know that this particular problem, they have already said that we are not going to print anything. So instead of doing cout root data, we are going to store the particular value to be printed at this position into the array. So we write output.pushback root of data. Fine. So the only difference is, instead of printing the root node's value right now, just push it into the array. Right, so we are storing that particular value into the array. This is what we now want, isn't it? Now, what is the next step? We know that the algorithm said first of all print the value of the root node, and then before moving to the preorder traversal of the left subtree, store the address of the current node. So right now the address of the current node is 1, right? So what did we do so far? This is an output array, and so far we basically store the value 1 in the output array, and parallelly what we did, we will push this value into the stack. Okay, this is my stack, the address of 1. So address of 1 will basically be pushed into the stack. So for that what we write here, we write stack dot push the root node address. Now root is pointing to 1, obviously that particular address is pushed now into the stack. What next? Now the moment you push it, the next thing is update the root's pointer to point to the left node of this particular root node. So root should now point to 2. So basically we say root equal to root left, right? Root equal to root left. So basically now root will point to this particular node. So how long will this should this go? Until and unless we know there is a valid node or root is not equal to null. So that is why we basically put this entire code into the while loop. So while root is not equal to null. Getting the point? While root is not equal to null, we will basically perform these operations. Okay. So yeah. So while root is not equal to null, we will basically perform this operation. What is the operation? Print every element. Okay, print every element wherever the root is pointing, root node is pointing, basically the root pointer is pointing. and store their address into the stack and go on moving left, isn't it? See here, the same thing is happening. We are at point 2. So root left is 2. 2 is not equal to null. What happens? Control comes back to this particular point. Now output dot push back root data. So 2's data, that is 2 is be pushed here, and stack dot push root 2. So address of root will be pushed. So these two operations are done. Now what should happen? Root equal to root left. So again go left of this node also. So again this is no longer root. Root now is root now is pointing to 4. So again go back. Root is not equal to null. True, because it is a valid node. Output dot push back root data. So basically 4 will be pushed, and also stack dot push root. So basically address of 4 will also be pushed. What next? Root equal to root left. Now we know that the left of this is nothing but null, and once it is null, so it will come out of this particular loop, isn't it? It will not go inside, it will come out. Now what should happen if it comes out? If it comes out, we should basically check if stack is empty or not. So if stack dot empty, if our stack is empty, we should just break. Our job is done. Otherwise what we should do? We should update our root to point to the right node. Getting the point? Why? Because this will perform the right order traversal. And how long should this go? Again I'll be creating a while loop here. Okay, do this entire process of left and right traversal till 1. Okay, while it will keep on going until and unless my stack is non-empty. That is why I am using while 1 here. Okay, so the purpose of using while 1 is the same here. The reason why I am using while 1 is because I want this process to keep on repeating, iterating, isn't it? So let me put this in a nested fashion. Yeah, it looks fine. So this should be here. This is here. Alright. So how is it actually working? You see, our root node now is pointing to 4, and then it moved to this null, right? It was null, and once it was found to be null, I will check whether stack dot empty. So obviously stack is not empty. What will it do now? Now the thing is, this is root node is pointing to this particular part, and this is null. And if this is null, it will not go to the while loop. Instead it will come out and check if stack is empty. If stack is empty, break. But if stack is not empty, I skipped a step here. If stack is not empty, we should pop an element from the stack, right? So basically root will now should point to stack dot top, right? So if you directly write pop, that will be a problem, okay? Because pop operation will not return anything. It will just remove the topmost element from the stack without returning anything. But I want the address of A4 to be returned, and if you want to do so, you basically have to use stack.top first. So basically by this way you will get the value at top position, and then now you can remove the element from the stack. So following this particular operation, I can say stack.pop. Now you can remove it comfortably. Getting the point? So this should work fine. So what is happening here is basically, now this was pointing to null. Now if it is pointing to null, I'll not go inside. I'll come out and check if stack is empty. Stack is obviously not empty. So root equal to stack.top. So top is A4. A4 will be, root now will point to A4. Basically this point. Now again what will I do? Root equal to root right. So means do the pre-order traversal of the right part. Right is again null. Again null. What will happen? If it is again null, you see root equal to root right. This will again come inside. Because it is true, come inside. Root not equal to null, then do this. Otherwise again pop an element from the stack, because if stack is not empty. So obviously popping the element means what? This is already popped. Now A2 is on the top. So now the pointer will now point to A2. Getting the point? So now we are pointing to A2. Now you see, the moment I point to A2 the second time, this is already completed. Getting the point? Now what happens in A2? I will point to A2. The root is now pointing to A2, and then I am saying root equal to root right. Basically means right do the pre-order traversal of the right subtree of 2. Basically now root node is pointing to 5. The moment root node points to 5, again what will I do? I will come here and check if root not equal to null. Right? While 1 is always true, come inside. Root not equal to null. Obviously it is not equal to null. So if root node is not equal to null, what do? We push that particular element into the output array, which 5 will be pushed here, and at the same time push the address of 5 also. Remember, address of 2 is already popped out, right? So address of 5 is now pushed. Getting the point? It is pushed. Alright, root equal to root left. So left will also again be null. It will come here. Right will also be null. It will directly go to the, now root left is null. Fine. What will I do? If it is null, it will come here and check if stack is empty. Stack is not empty. Then root equal to stack.top. Pop it basically, right? Again I am coming back to A5. Now what will I do? Root equal root right. Again my pointer will point to the right node of 5, which is null. Again, if it is null, we will again come back and check if stack is empty. If stack is empty, break. If not empty, then pop the topmost element. Topmost element right now is A1, which means root now will point to A1. And again after this we are saying root equal root right, which means root now will point to 3. Getting the point? So please follow the dry run. So now root is pointing to 3. Now the moment root now points to 3, which means it is a valid node. If it is a valid node, what we do? Output dot push back root node, means 3 is pushed. The address of 3 is also pushed. So right now we no longer have anything called A1, because A1 has already been popped out, right? We have A3 here. We have 3 here, right? A3 pushed into the stack. Now what will it do? It will now say root equal to root left. Root left is nothing but 6. It is again a valid node. So valid node, so again it will do output dot push. So 6 will be printed here, means stored here. And again the address of 6 is pushed. The moment address of 6 is pushed, it will do root left. Root left means pointing to null. If it is null, what happens? It will check if stack is empty. Not empty, then root pop. Pop and show in root. Pop means A6 is popped out, pointing to A6 right now. Just after pointing to A6, say root equal root right. Again pointing to the right side of A6. This is again null. If it is null, what do we do? If stack is empty, no, obviously stack is not empty, because right now we have A3 here, right? So what will we do? Root equal to stack dot top. So root is basically pointing to A3. So root will now come back and point to A3, and now we'll say root equal to root right. Right? So pointing to A3 means this is already popped. So now root equal to root right. So root right means 7. So we'll now come to 7. 7 is a valid node. Push dot data. So 7 will be pushed here. The moment 7 is pushed here, what will we do next? Stack dot push root 7. So address of 7 will be pushed here also. Root left is null. If it is null, we know what to do. It will not go inside. It will rather check stack is empty or not. If stack is not empty, then root equal to stack dot top. Come back to 7, pointing here. This is done. Root equal to root right. So right of 7 is again null. And if it is null, this is already popped, right? Popped. If it is null, then what will happen? It will just check if stack is empty. So again, definitely stack is empty right now. So if stack is empty, we just break. So break means we see just come out of the entire process, entire function. This function, and we come out of the entire loop, and finally the function will end. So if the function solve ends, what will happen? The control now moves to this particular function, right? Let me just erase it. The solve function has already completed its job. So the control now moves to this particular function here. So now we will be basically returning output, because the traversal output is basically stored in this particular vector array. And before that we will say output dot clear, right? Fine. So what happens is basically we will be getting the root node from this particular function. We go inside, clear the output array. Initially it is cleared. Then we will just call the solve function. Solve function will do the entire traversal approach without using any recursion. You see, this is how we explain right now how it is working. And finally it will be completed. It will come back here and it will return the output. So basically this code should work here in this particular case. Let us see how it is working. So yeah, let me just run the code. Yes, it is fine, it is working. So let me just submit the code and see. Well, that's it. So we got the output, and this particular problem works fine. Very important problem. We should know this, how to perform the traversal without using recursion, and very important problem from placement and interview perspective. So that's it from my side. In case of any doubt, please put it out in the comment section, and please like, share and subscribe. Thank you.